Okay, so as I said earlier, this is an opportunity to sort of think about some of the things that have come up during the conference through people's presentations, and in particular, the sort of commonalities that might be shared or where we think there might be some interesting synergies in different areas. And I mean, I know that Marina, when I first met her, and that was at the Geneva magnetospheric boundary meeting, I think at that time you were solely into young stellar objects, if I'm not mistaken, but now you've expanded into X-ray binaries and other things. So there is all of that sort of physics of the magnetosphere, but I think the really obvious one, and that's one that, of course, Poshak alluded to just in his talk, is, you know, jet launching. And we know that there's jets on all manner of objects now, from the, you know, blazar jets, X-ray binary jets, cataclysmic variable jets, and protostellar jets as well. Now, of course, there's huge orders of magnitude in the parameters that are used in, well, that describe these jets, but nonetheless, let's sort of start off there. So, is there anyone on the SOC who would like to say something? And I'll pass the microphone on. And I think it would be good if all of us had some inputs, and then we'll just open it to the floor here and, of course, to the online participants. So, Marina, you want to do? Or?
I can. Yeah. Right. Sure. Yeah, so it was a story like 40 years ago or 50 years ago when Richard Lovelace proposed the model of magnetic jets. He didn't get any grant because people say magnetic field is irrelevant. You just take a hose, press it, and it flows like water, okay? But years passed, we got grants, but in other area like accretion to a star with dipole field, lots of grants, because people know there is a star, there is a field, and so on. Anyway, in respect of jets. And now you can take any astrophysicist on the street and ask how to form a jet. And any astrophysicist will say, I need just rotation and magnetic field. That's it. So, problem solved. Yeah. And my understanding, maybe I missed something, that whatever object you take, Titori stars, like Zani gave a talk, wind is driven by magnetocentrifugal forces, or you can go to larger scales, to black holes, blazars, or you go to gamma ray bursts. Everywhere, rotation plus twisted magnetic field drive a jet. And of course, the power of a black hole, it's also rotation contribution. So basically across the scales, we see that magnetic field determines launching of the jet and often radiation. In this, I mean, reconnection was important issue in and I think people did very good progress in understanding reconnection and its role in dissipation of energy, magnetic energy, because magnetic energy is not visible. You need to see radiation, and reconnection is important process. Okay, maybe I'm talking too much. Let me give to other people.
I can just maybe mention a couple of presentations on this issue by Gipa Masuke and Akiro Inoue, where they applied these general relativistic MHD simulations to jets to show the launching mechanisms and the angular momentum and magnetic transports. I just think that the level of sophistication that the modeling has reached in the last couple of years is really tremendous. And I mean, at the moment, I think we are at a level where the modeling are starting to challenge observations. And I think this is what this conference really brought out, is that there is now a synergy between the observational astronomy and the theorist. And obviously this will lead to a very healthy competition that will drive the field forward.
I mean, Poshak said this in the two things that he mentioned, jet launching and MHD models. and the fact that these very sophisticated MHD models, are they going to predict things that we should go and look for observationally? And I don't know, Poshak, since you raised it, if you have that, you know, if you have any comments on that, if you're hearing me.
Can you hear me as well?
Yeah.
Okay. So yeah, I think we could be here for the rest of the week or another week discussing this in detail. But I think one of the issues, based upon my observer-based understanding, I'm not a simulator or a theorist, is that these models really are amazing, the simulations, but they still struggle to simulate properly both the magnetic fields and plasma flow and radiation. And of course, we observe only the radiation. We don't observe the underlying magnetic field sort of scaffolding, if you want. And so the interplay between these different aspects still needs to be simulated. But please correct me if I'm wrong. If this has already been done, then I'd be really happy to hear about it. And secondly, in terms of time-dependent modeling, again, I'm not aware of how far these models have evolved in terms of really being able to follow the incoming accretion flow in detail. I know people are able to simulate accretion and outflows in terms of the wind-dominated outflows on timescales of hours or longer. But whether we can follow the intricate details on much shorter timescales, more relevant to the inner accretion zones, that's still unclear to me.
I also have a couple of comments about computational astrophysics. Actually, we saw a lot of numerical models and different applications to different objects. I mean, intermediate polars, GRBS, and accretion, protoplanetary disk, and etc. But actually, it is clear that all our numerical models has a quite poor physical basis. All models, I don't know, maybe not all, but many of them, but for me, it's all models need more deep physics. And it was a good surprise for me that during the conference we saw a lot of physical reports. I mean, Richard Lovelace, who told us about Rossby waves. Because Rossby waves are inertial ones and they should transfer angular momentum and energy. And it's extremely important for accretion disk. Alex Lazarian stressed our attention for reconnections. Jean-Marie told us about a new instability. Pete just told us about a new model of the IE aquarium, and it's I think it's a great deal that we can speak each other during the conference, and I hope it will help to improve our numerical models.
Yeah, I just wanted to comment on something. I think in this conference only one time it was mentioned by Marina, a laboratory experiment that we can make with respect to the plasma we observe onto compact object in other place. This is a extremely fast developing part of the physics, and I think in recent time we will be able to do astrophysics in laboratory. That means we will have not only observation, we'll have simulation and laboratory experiment. And those three are complementary approach. And maybe next conference may include this new community. The laboratory experiments are done with different kind of process that we know. They're using power laser. Sometimes they do Z machine with pinching process. But the fact is that you can reproduce at present plasma we observe. For instance, on two white dwarf, we were modeling this with the Lully laser in Paris. And this reproduce by means of scaling law exactly the same equation you have. That means once you design an experiment, you can just tune every parameters you want and see the results. We are not at the level that is always reproducible, but now we turn to very high power laser, the megajoule laser. There's one in the US, the NIF, and the other one in France, LMJ. And I think this way of investigating the physics with high temperature plasma is very promising. And I think probably the conference next time will be including those people too, that because they are lacking information of what kind of problem we have to solve. So they don't know what to do. And they have already extremely efficient tool of diagnostic of those plasma at the nanosecond scale, because it's a question of irradiating a millimeter target with a high energy laser. And everything evolves in nanosecond scale, but you have enough instrument to watch what's going on at the nanosecond scale. And those instruments exist, and they are just making science with them, but they don't know what we need in astrophysics. I mean, in general, I mean, some projects are already developed, the jet and things like that, but more and more people can do experiments now in the lab for astrophysics.
Maybe just to add under an observational point of view, that these measurements for magnetic field still really require polarimetric observations, which actually now are going to be very, very important, but at the same time getting to the good sensitivity. So under this point of view, that will be crucial. For example, what has shown Poshak, these very rapid variations and seen in the in polarimetry.
I would expand that to say just ordinary photometry as well. I mean, we've seen how much TESS and K2, Kepler, have been a game changer in terms of getting continuous observations over weeks and weeks at high cadence. Just imagine if we had a cadence of sub-second with a facility like that, you know, what we would be able to do. And I'm just going to mention here also the Rubin Observatory, which a couple of people have mentioned. So although Rubin wasn't designed for our community, as we know. So it has other science drivers. Nonetheless, as many of you probably know, there's a transient and variable star collaboration within Rubin and stars Milky Way and local volume. And there are compact binary people and other communities, protostellar people involved. And despite the fact that, I mean, Rubin is a big aperture, high étendue telescope. It can reach great depth, but it's still at a single site. It's still only got a cadence of, you know, a couple of observations in a filter per night of 15-second exposures, and then maybe a few nights later, another couple of observations. But it goes on for 10 years. And we've already learnt from, actually, Tom Marsh, and I'll say some words about Tom at the end, but he astounded a number of us in his Nature paper on AR-SCO, where he analysed 7 years of the Catalina real-time survey data, modest-sized telescopes observing AR-SCO, maybe 3 or 4 exposures a night of 20 or 30 seconds, and that's it. And then a few nights later, some more observations. Who would have thought that you could pull out of that data a power spectrum that showed a clear modulation at 120 seconds? And yet it happened. And so that's one of the things that I'm interested in, with the potential for Rubin to do the same. not just looking for things that are variable on hours and days and months and so on, but looking at really that sort of tens of seconds. How short it can go, we really don't know yet, but this is something that can, of course, be simulated, and so we will see. But I think these facilities of the future will really give us a huge amount of information. Yeah.
I would like just to add that Plato will help a lot. Plato. Sorry, Plato. It's sort of big, it is a mission that is supposed to be launched within 2.5 years. And it will look for starring in a, there are 2 positions still discussed, but those regions of the sky will be monitored for a long time. Checked, there are a number of X-ray binaries, CVs. I already checked there.
What time resolution?
A second or so.
Really? Great.
I absolutely agree with future, in nearest future we'll get a lot of information, but my personal feeling that even now we have a lot of observational data and you cannot interpret it properly. So.
Yeah, I have a brief comment. So initially I started preparing my talk for Titori stars to compare TESS light curve with a numerical light curve. I thought, what's amazing, 1 month of like a 10-second cadence observations. But then by accident, I decided to check what SALT is doing. And I was shocked that TESS can do 80 millisecond cadence. And it's just amazing. You can do a lot with this time resolution in sense of photometry. So it's just a very, very, very nice like telescope.
I think we should now open to the floor, both people in person and also online. So would anyone like to take up this conversation and make any observations or comments? Please, if you do, come to the microphone here. So it's all of this is being recorded, by the way, for posterity. So we can all go back later and look what we said, you know. Yeah, it's being videoed, yeah. So please, don't shrink back. Come to the microphone and say your 2 cents worth.
I wanted to mention a topic of interest to me for a long time was connected with Vera Rubin, dark matter. I'm wanting to know, is there any evidence of dark matter stars? And what other evidence, other than gravitational lensing, is there for dark matter? I think it's a fascinating question. There must be, there is undoubtedly this gravitational interaction between dark matter and baryonic matter. And I'm just interested in the observational aspects of this topic.
Thanks, Richard. Run, Phil.
I just wanted to add, this is a small caveat about the discussion of Rubin and LSST, because given the interests of almost all of us at this meeting, and this idea that we're going to get the opportunity to do it on many of these sources, and what Tom did with ARSCO, let me remind you of, it was several years ago, Mike Shara and I were at meetings discussing the fact that there's something, you have a problem. Every high mass X-ray binary in the Magellanic Clouds, I believe, will be saturated in LSST under the observing cadence. It's about 13th magnitude or so, which means ARSCO, forget it. And a lot of things like that.
I think that's certainly the case for the deeper, wider, faster normal survey data. I don't know if that's necessarily the case for for some, what are they called? There are nominally plans for shorter exposure, dedicated, not deep drilling fields, but I've forgotten the term.
Yeah.
But you're right. I mean,
For the general survey, it'll be fantastic, but for the fainter objects, it's going to reveal lots of objects that we don't know anything about. Yeah. But just don't think your favorite object is going to be fantastic.
And yes, you just use the U-band data.
Yeah.
James, did you? Yeah.
Yeah, I would just like to take it off from a different perspective, to just comment on what my impression of this meeting was. I'm a radio astronomer, and I listened to quite a number of the talks, and I saw quite a few things that we are struggling with in radio astronomy, which you already have developed a lot of models on how to explain, like things like periodicity and using magnetic field to explain a lot of things. So what I would like to say is, in 10 years' time, I would like to see more cross-pollination between other communities. Of course, astronomical observatories and the optical is evolving, the Rubin Observatory is coming, but we are also making a lot of progress in the radio side. We're seeing lots of things we don't understand, especially with Meerkat. We have these bulge coming out from the center of our galaxy, which we don't have explanations for. We're seeing compact objects with properties we don't ever know. And a few of the things you are already developed in this community can be transferred there. A few of the answers to questions you have could come from what we have from radio astronomy. So I'd like to see more transfer of knowledge between the two communities. That's all.
One can only imagine what we will be discussing at the meeting Poshak's going to organise in 2033 with SKA now being operated and CTA and the rest. Are there any comments from our online participants? No? Any more comments from the floor? We're winding down now, and I know it's the end of the day, and probably a lot of people are just wanting to get. Oh, Poshak, you're there. You want to say something?
Yeah. I'll be resting on a beach somewhere in 10 years' time, not organizing meetings, I don't think. But sorry, okay, now I couldn't previously see the feature to raise hands, but I think it's now appeared. I agree with many of the comments that have just been made. The need for fast polarimetry, the need for absolutely fast photometry in general, the fact that we already have too much data. I agree with all of this. I'm not sure where the most important discoveries will come from. But one of the things which I do know is that we really struggle with, in the particular field that I talked about, and David, you've been deeply involved in this, is we do have a lot of data, but what we don't have a lot of is simultaneous data. So we've only investigated one dimension in some respects, and in particular, strictly simultaneous correlated data, which is really needed for many of these investigations, especially black holes, which are particularly broadband emitters, but not only. I'm sure a lot of that has been discussed in this meeting. We really lack that. So looking beyond, looking to 10 years' time, I know we'll have a lot of these facilities, but actually coordinating them might be even more of a nightmare. And as Bill said, many of them may or may not, they'll just be too sensitive for our needs, perhaps. Maybe we need to look even further beyond. My own dream is actually looking to the moon. Maybe not in 10 years' time, maybe in 20 or 50 years' time, we will have a moon base. And there, the nice thing is that you can get long interrupted nights, very long interrupted nights, uninterrupted nights, and you can put all your favorite wavelengths on the surface of the moon. X-rays can be done from the surface of the moon, optical can be done from the surface of the moon, infrared, radio, everything. So that's brilliant. Of course, there will be other issues as well to do with dust on the moon, etc., etc. But maybe that's what we should be. That's where we should organize our next conference. Phil.
On the moon, yeah.
Yes.
So, yeah, I mean, you're completely correct. And it's probably worth mentioning something which a number of us in South Africa have been involved with in recent times. And that's the idea of harnessing smaller aperture telescopes globally in a coordinated network that could do effectively what a lot of science was done in the 90s that Chris Clemens alluded to when he gave his talk to Dara about Dara on the Whole Earth Telescope, where you get continuous coverage. So there's a very ambitious program which some of you may have seen something about in a magazine that's been floating around on BRICS Astronomy, and that's something called the BRICS Intelligent Telescope and Data Network. And BRICS, for those who don't know, is the collection of countries involving Brazil, Russia, India, China, and South Africa. And we all have our existing facilities, and also we have plans for developing future facilities as well. So in the sort of immediate plan for this project, which has already begun, particularly being led by South Africa, is developing this sort of idea of an intelligent observatory, which is triggered by event brokers and observing marshals that decide what sort of observations will be done. That's doable right now. We have the technology to do that, and we're starting to do it. But the grand plan for this, if we are successful, is to develop also a new build of telescopes, and you may all be highly skeptical about what I'm about to say, but the sort of phase 2 of this 9-year program is to build 70 1-meter telescopes with 25 square degree fields per telescope, covering 4 pi steradians of sky. So they'll be situated multi-longitude, multi-latitude, and with an array like that, we have the potential for having a cadence of variability on the sky, detecting variability on the hour time scale, and of course faster if the instrumentation, the objects are bright. So these are sort of ambitious ideas, and we're not the only ones thinking about such networks of telescopes to exploit these large surveys that are coming, like the Rubin Observatory, but many other surveys as well, like, you know, the eRosita that we heard from Axel and others. Phil, you wanted to say something?
Yeah. Actually, I was going to start off with Poshak said, but it's going to grow into what all of you have now said. I agree with Poshak completely. The real breakthroughs have always come when we've had exact simultaneity. It's just bloody difficult to get that across all wavelengths. And you and I have been involved in trying to organize that kind of thing for a very long time. Moving it all to the moon, well, that will not be working in 2033, so maybe that will save that for the 2043 meeting, even though we might be driven to do it sooner at the rate that the night sky is being destroyed by the same people that give us this launch capability. But anyway, I'm not going to go into that. Stepping back, David, because I was going to talk about this ability to observe things continuously. I only had a short presentation, and I did say I can't talk about this. I gave that plot.
You can't give another one now.
Oh, damn. The Maxi J1820 overview, and I talked about the optical light curve. I didn't stress enough how much data there was in there, and we didn't organize a thing. It happened because of the large number of amateurs who now have equipment that only a decade ago, any of us would have said, wow, yes, I'll use that. The costs have come down. And some of them have a computing ability linked with it, that if we could start to link those together, we're talking about hundreds of people, relatively small, but there's a potential there literally now. It all comes down to the software of linking them together to make these things work. Many of these guys, I think, I know one of them because he's got a telescope on La Palma, not at the very top, but still quite respectable. And he would love to do things like this because what you were describing is kind of like Meerlicht on a slightly larger scale. That's achievable by 2033, and I think that would be absolutely fantastic. But let's look at what we can even get going right away now on the optical side.
Thanks, Phil. I believe we've got an online question.
We've got a couple of online comments here. The first one is from Jean Luna, who says, my computer audio isn't working right, but I would like to call your attention to the new set of filters available on the Gemini telescope, which are centered on the Raman 6830A scattering band, which will be a unique feature from the symbiotics. So in order to discover more of these, the filter is great. And if you suspect of the symbiotic nature of an object, you could observe with this filter and see if it is of the nuclear burning class. It is cheaper than spectroscopy. And then we have another comment by Paul Barrett, who is online. I don't know, Paul, if you're there, do you want to unmute yourself and make the comment, or should I read it for you?
Can you hear me?
Yes, we can.
Okay. I was hoping not to, but you've encouraged me to do so, so I will. Yeah, I mean, I work in radio astronomy, or at least that's my focus nowadays, and I have a lot of data, radio data, which unfortunately has not been published. I've been trying to get it out, but there's a lot of it going on. But the one thing I noticed is, in terms of radio astronomy, we're just, in terms of like X-ray astronomy, we're photon limited, we're signal limited. And I see, variations in my data on sub-second timescales of polarization and photometry, and, SKA and NGVLA, when they get down to sub-microjansky sensitivity, will hopefully allow us to actually, see what's going on at those timescales and, across the spectrum. So I'm really kind of excited about that. So, we'll see.
Thanks, Paul. Okay, we don't have any other online questions, Ruby?
No, that's right.
Any further? Yes, Joe, you had something?
Yeah, I thought I should just give one comment, there are a lot of active developments happening in the instrumentation, like those superconducting detectors, etc. And I feel like it will be really exciting in a decade or so that we can actually do spectroscopy as cheap as photometry, because these have energy resolution, pixels and all. So I think that'll be fantastic and a game changer when those technologies become really cheap and easier to use.
I agree with you, but I must say I'm somewhat pessimistic, because I remember at the beginning of SALT, I actually was in discussions with people at ESA about the superconducting tunnel junction cameras that had been developed there, and there was a prototype actually used on the WHT. And nothing really has followed from that, regrettably. I think maybe because it was sort of, it was ESA, so it's space and not ground-based. And of course, there are other types of, apart from STJs, there's other technologies. I mean, yes, that's really, wouldn't it be lovely if we could throw away our gratings and just have a detector that could tell you not just the time and the position of a photon, but its energy. Although we would never get to the resolution of energy, I think, that we would want, that a grating would give us. But yes, we look to those people involved in those technologies. And I know there's all sorts of other similar technologies, transition edge sensors, and something Kieran O'Brien was involved in, which I've forgotten the name of the type of instrument, maybe Poshak. Do you know what that was, the instrument that was being developed for energy resolution? Phil knows, so yeah. But, you know, these things are not easy technically. I know for the STJs, you know, it was helium cooled and it was like a massive instrument at the Naismith focus of...
I know, it's like a mainframe computer in size.
Yeah, for like a, was it a 3x9 pixel detector or something?
Indeed, and you're right, we had that on the WHT, but they never managed to get it to a practical size. Kieran is working on microwave kinetic inductance,
that's it.
squids and things like that.
Right, yeah.
And they are certainly a lot more compact. He's had things working in California. It's still 2 or 3 years away, but it's heading in a much more practical direction. And good enough. No, so not a grating, but a heck of a lot better than a broadband filter.
Yeah.
So there's a definite possibility.
And I think certainly having photon counting detectors for polarimetry, where you know your Poisson noise limited, and you can essentially run them as fast as you record, gives you the flexibility. I mean, Steve Potter's built an instrument here called Hippo, a photopolarimeter that samples every millisecond. So anything longer than, well, I think it's 100 times that, isn't it, Steve? But anyway, it has that ability to do, and so. You know, that's something you can't do with a conventional polarimeter with a, you know, clunky wave plate rotation and a CCD readout, which is fine for measuring the polarization of a galaxy, where you don't care whether the thing varies in a year or 100 years because it doesn't change, you know. But for fast stuff, the CCDs are pretty useless, Okay. Any other comments from the audience? No? Final comments from anyone on the SOC? No? Good.
So I know that David, in his rationale, he wrote that he wants to organize meetings similar to that which was in 2014 in Geneva on magnetic fields. And I would tell that this meeting is better than one in Geneva. It has very broad like distribution of talks on different scales and well organized and excellent speakers. And we theoreticians, you say we are good, but we need to learn more of observations, lots of observations which we miss. And observers are learning from theorists, also important. So it's just overall very good meeting, and thank you very much, Dave.